Hello, my name is Andy Huang, and I'm going to be solving question 2 of homework 9. So for this question, we're given a circuit, and we're tasked to find the power being supplied by this source. The key idea is knowing that the power delivered by the source is going to be the power absorbed by the rest of the circuit. So we're already given the power of the load. The problem is finding the power of the network. We know the impedance, so all we have to do is find the RMS current. That way we can use this formula to find the power of the network. So how to do that? Let's start with finding the equivalent power of the loads. So for do that, we're going to be using the law of conservation of energy and just summing them up. But first we need to find the rectangular forms of the complex power, of the load power. Let's start with load 1. We know that load 1 absorbs 10 kilowatts of power with a power factor of 0.8 lagging. To find the complex power of this, first we need to find the angle of the power, which is going to be the arc cosine of the power factor, 0.8. Plug that in. Get an angle of 36.87 degrees. And the magnitude is going to be our real power divided by our power factor. So that's 10 divided by 0.8. And we have an apparent power of 12.5. Now this is in polar form, we need to convert it to rectangular. So if you're using the TI-84 Plus, it actually has trouble converting from polar to rectangular, I found, if you're using the e to the power of a degree times I format. That's because for some reason it will always, if you put in a degree into the exponent, it will always interpret it as radians, even if you have it in degree mode, as you can see. So let me show you something. Let me show you an example of like e to the power of 60i. It spits out something completely wrong because it's seeing this as radians instead of degrees. So you have to convert to radians, which is really annoying. But an easy way I found to do it is to save pi over 180 into some variable using the store command. And the variable I like to use is this theta symbol down here by 3. So I just save that into theta, and now if I try this time converting it to radians, it gives me the correct value. So now I can do this and convert from polar to rectangular, 36.87. And I got 10 plus 7.5J. Okay. So that is the complex power for load 1. For the sake of time, I'm just gonna give the complex power for load 2 and load 3 because they're basically done in the same way. Just note that for load 3, it gives you a power factor of 0.5 leading, which means you have to take the negative angle of the arc cosine. So for load 2 and load 3, we got 20 minus 15J kilovolt amps. And for load 3, we got 15 minus 25.981J kilovolt amps. Now the total power of the loads is going to be S1 plus S2 plus S3. And when we sum that, we get 45 minus 33.481 J kilovolt amps. Now that we have the power, the total power of the loads, we can use this V RMS value to find the current using this formula right here. So 45.1J times the V RMS, which is 500. Okay, I RMS, the complex conjugate of that. Solve for I RMS, and we get a value of 90 plus 66.962 J amps RMS. So that's the rectangular form. It's actually more useful for us to have it in the polar form because that gives us the magnitude. So if we convert that into its polar form real quick, we get 112.178 with an angle of 36.65 degrees. All right, now that we have the RMS current, we can find the power of the network. So the power of the network, using this formula right here, we have an RMS value of 112.178 squared, and our impedance is 1 plus 2J ohms. When we calculate that, we get a complex power of 12.584 minus 25.168 J kilovolt amps. Now that we have the power of both the network and the loads, we have the power of the source, because power delivered by the source is going to be equal to power absorbed by the load plus the power absorbed by the network. So let's plug that in. Power source, this one and that one. If we add those up, we get a value of 57.584 minus 8.313 J kilovolt amps. That's the rectangular form of the complex power. Let's convert that into polar real quick. If we do that, 58.181 with an angle of negative 8.215 degrees. Because we need this angle to calculate the power factor. Power factor is going to be cosine of that angle. Which is going to be pretty much 0.99. So now we have everything we need to solve this problem. It's asking for the complex power, which is 8313J kilovolt amps. The average power, which is the real part, in kilowatts. The reactive power, which is the imaginary part. And the apparent power, which is the magnitude, which we found over here, 58.181. And the power factor, and this is going to be leading.